Okay, I want to finish up section 14.2. We got to the point where we said the change in kinetic energy is equal to the work from 1 to 2, and we also saw that the work from 1 to 2 can be defined after integrating to be 1/2 mv final squared minus 1/2 mv initial squared. We can take this and put this on the other side to get 1/2 mv initial squared is plus the work done from 1 to 2 is equal to 1/2 mv final squared. Now, okay, this is what we call the principle of work and energy. And we're going to replace the kinetic energy with a T. So we'll call this T1 plus the work from 1 to 2 is equal to T2. Okay, now 14.3 starts talking about the same exact law except for systems. Now what does that mean? That means we can draw a box around the problem or the system, and everything inside it is what we call the system. The book gives you a little diagram of some body that's maybe moving on a path. They give it a tangential coordinate, a normal coordinate, and they say that there's a bunch of forces acting on it externally and internally. So the capital F is the external force, and then maybe some internal forces, and these could do work. So we have to say if it's included in the system, since they're scalars, all of these things are scalars. T1, the kinetic energy, the work, they're all in the same units, right? They're all in joules, they're all scalar, that we can take the summation of them. So this equation will become the summation of the T1s plus the summation of the work done from 1 to 2 is equal to the summation of T2. So we could have multiple particles in the problem. And then there's a nice little excerpt on sliding friction. So sliding friction would be a case where we have some frictional force acting, and maybe some force P pulling it, and it is maintaining a constant velocity in this problem. For it to do that, for this mass to maintain a constant velocity, that means that the frictional force has to be balanced or equal but opposite to that force P, right? So the magnitudes are equal. If that's the case, we can say that 1/2 mv initial squared plus this force P times S, this is work, and I'm going to start putting all the work done in brackets on these problems. Friction acts in the opposite direction, so we're going to say mu k times the normal force times S, so don't forget to multiply the distance the force works through. That's how we get work. And that's going to equal some 1/2 mv, and we maintain velocity. So the problem we're looking at right now is the fact that these two things are balanced, and by them being balanced, we actually maintain a constant velocity. It doesn't have to be the case, though. Friction is not a function of velocity, in our problems at least. Okay, and then it goes into a very interesting part. Take a look at I recommend reading it. You want some good, very simple reading, no numbers. It starts off with, indeed, this equation is satisfied by, and it's under the work of friction caused by sliding. I'm going to tell you about it, but I think reading it from another person's perspective will help you. So what they say is that indeed this equation satisfies the fact that these two things are equal, the frictional force and the force P, to maintain a constant velocity. But what's actually happening is if we look at two surfaces, and I'm going to draw some roughness on there. So here's maybe the bottom of a block or something, and here's our other surface. This could be the ground. Alright, there's going to be these little micro deformations or molecular deformations that happen, and little pieces are going to move over. Some are going to get dislodged, and what happens is we're going to see that the distance s that P goes through, or the work done by P, is going to be different than the work done by the frictional force, because the distance P works through is s, where we can call the distance that the frictional force works through some s prime. And s, due to those deformations, s is greater than s prime, and we should really be noting that loss, okay? We have some, it's mu k times the normal force times that s minus s prime. And that difference right here ends up being what we call a loss of internal energy, or a gain in internal energy, I'm sorry, an increase, or heat. So it's kind of interesting. In general, we're not going to deal with heat in these problems at all, unless maybe it says 20 joules are lost to heat. We're not going to calculate the heat loss. We're not going to worry about this right here. We'll just worry about how far the normal force works through. So to wrap up, I don't even know if your book talks about this. The work by friction would just be equal to that frictional force integrated through this distance s, from s1 to s2. So if it's a function of s, you'd integrate it. Otherwise, you would just have mu k times the normal force, integrate s from s1 to s2. Alright.